Hello, welcome back, and we are going to listen to the third lecture by Wadey.
Okay, so yesterday I gave some motivation for the BPS algebra, and I defined the quiver-Yangian. So in this lecture, I will try to explain that when the quiver-Yangian is a BPS algebra. Yeah, I think I won't be able to finish in just one lecture, so I probably need Friday as well. So today I think I'll focus on the quiver that comes from the toric-Clavier threefold. And they have the property that the BPS states, which are representation of the quiver-Yangian, has a description of some 3D crystals. And on Friday, I'll move to general quiver. So for the general quiver, you lose this crystal structure. So instead, we have to describe the BPS states as some ideals of the Jacobian algebra. So I'll define what is the Jacobian algebra later. But to make this generalization easier, today I'll start by explaining where does this ideals of Jacobian algebra come from the physics setup. And then I will use this toric-Clavier case to explain why in that case you have a crystal structure. So that will also give you a nice way to visualize these ideals. Okay, so the focus of today is we consider the type 2A string by generic toric-Clavier threefold. So toric here means that there a U1 cube action, and so the Clavier here is the Kähler manifold with first chain class. You could vanishing first chain class. So that means it's Ricci flat. That there exists a complex matrix so that you can find the Ricci flat, so that the Ricci tensor is 0, and so this. And it has SU3 hologamy. That means that it preserves 1/4 of the supersymmetry. And the threefold here is a complex 3-dimension. So that means that so the 2D string is 10-dimension. So that means we'll have 10 minus 3 times 2 equal to 4. So we'll have a 4-dimensional theory. With so now we want to look at the half BPS sector of this theory. So the half BPS sector are given by the Debrien bound states. So in this type 2A string, so you have all the different even numbers. So we'll have D6, D4, D2, D0 brane wrapping holomorphic 6, 4, 2. BPS sector will be consist of the deep bound states of this D6, D4, D2, D0 rapid holomorphic cycles of even cycles of Clavius-Swift. And so to start with, we wouldn't need a D4. So we will have we will just have one D6 and no D4, and some number of D2 and some number of D0. So this I characterized means that it is in the I's 2 cycles. So here we just need one D6. That means that we're considering rank 1 Donaldson theory. So once we get the BPS algebra, then you can add this D4, and then you can maybe not in this series of lectures, but you can see that will correspond to some truncation of the algebra. Okay, so now
D4, can all be together with D6 as the containing these D4, D2, D0.
Yeah. So to start with, we consider the bound state of the just one D6, and then the bound state is D2 and D0. The bound state. You're turning on some non-trivial field.
Inside D6.
Yes, yes, yes.
Otherwise, the BPS condition will further break. Won't be harmed.
Yes, exactly. So it's exactly. So it's this bound state.
As a common word volume, which is 1 plus 1.
It's 0 plus 1.
Yeah, 0 plus 1. Yeah.
So exactly. So we want to look at the word volume theory of these different bound states. So that will be the intersection of all these points. So that will be 0 plus 1 dimension. So this, because it's the smallest one is D0. So that means that we have a quantum mechanics. So now, the number of supersymmetry we have is so to start with, we have so because it's type 2A, we have 32, and then it's let's write it this way. So this because it's type 2A, and we're on a toric club. On a generic toric Clavius-3. So the toric Clavius-3 condition means that you only have in preserving a quarter of supersymmetry, and then you're considering half BPS sector. So that means that in the end we have only 4 supersymmetry left. And so this is for a generic case. So for the special ones, you can actually have more supersymmetries. For example, if you're in this class, that means you're preserving. You can have half a supersymmetry, and if it's a C3, you don't break any supersymmetry. So that means for these 2 special cases, you can have a further symmetry enhancement. Supersymmetry enhancement. So we have 4 supersymmetry. That means that we have it's into 4 quantum mechanics theory, and it's a quantum mechanics theory. That's described by a quiver. So the quiver that I explained yesterday. So remember that. Yeah, remember that the quiver has a bunch of vertices and arrows between these vertices. So for each vertex A, that will correspond to a UN gauge group. And for arrow that goes from A to B, that will be a chiral bifundamental field. That transform with respect to, so this is A to B, so there's a UN A gauge group for this A, and then this is a UN B gauge group for B, for the vertex B. So this this arrow will correspond to a bifundamental that transforms with respect to this this UN group. And, so now from the so we start with the toric labiosity. So we need to translate this toric data to this data of the quiver and quantum mechanics, quiver and the superpotential. So so this map is one to many. I mean, in general, one to many. So there's for one toric labiosity, there can be more than one choice of the quiver and the superpotential. So this one to many, that will the so-called toric duality that corresponds to the cyber duality on the gauge theory side. So I won't have time to explain the detail how to start from the toric data to get the data of the quiver and the superpotential. But there's some physical way of doing this is so-called brain tiling. That's it's very efficient and physical. And so, for example, for the C3 case, this is the toric data, and the quiver is what we explained yesterday. This is a 3-loop quiver with this potential.
Excuse me, do I understand correctly that we just from this toric data we build the quiver that it fully determines it?
Mm-hmm. It's not fully determined. I mean, you
okay,
have.
You said it's like one.
There's one to many. Yes.
Okay.
I mean, that's for a more complicated case.
Mm-hmm. And once again, how we determine vertices and arrows of the quiver?
Right. So this is given by this brain tiling techniques.
Mm-hmm.
And there's also some more mathematical way of doing this, but this is some fixed procedure.
Okay. Okay. Please keep the right backward for a moment.
So that's the diamond tiling way of doing it.
Yes, exactly. Yes. That's
one to many you are saying? I thought there is a defined set of cyber duality which tells you how many are there. You can't just.
It's not one to many. I mean that it's possible to have more than one equivalent superpotential that correspond to one toric. And I mean, this say
Those two quivers should be related by cyber duality?
Yes. I mean, for those quiver, we have a conjecture that the algebra should be the same. But you see that the quiver itself looks very different. So it's not easy to prove. I mean, for some special cases that maybe I can explain later. But for special cases, it's easy to see, but it's not easy to prove. The more examples, maybe I'll think later. Right. So here you see this this set of character by fundamental. So they will give you a what dimension representation of the quiver. So now we have some more conditions. So you see that for this phi that corresponds to the IAB. So that's an NA by NB matrix. So that means that if you want to take the product of the two fields, you can only do that if you can only take the product of phi I and phi j if the target of I is the same as this. So that means that you can only do it if say this is from A to B, and then this j has to be from B to something else, B to C. So that means that this phi I is actually a representation of the Jacobi algebra. Sorry, I should first say that it's a representation of the path algebra. So the path algebra of the quiver is so the elements is all the path is given by the path that you build from all the arrows. So a path, say from A to B, from C. So it's
do I understand correctly that these bifundamental fields are in this representation that you described?
Yeah, it forms a representation. So I mean, because they can only multiply when the arrows are aligned, so they give you a representation of the path algebra.
Okay.
So the path algebra is just so the elements is just all these paths that are built by the product of the arrows, and the product is just a concatenation of the of the path. Not P. So in this set, into 4 quiver quantum mechanics, we also have the F term. F term constraint. That's given by the derivative of the superpotential being 0. So let me give you an example. Let me first explain this by example. So for this case, for the C3 case, so we want to look at the all the derivatives here. So this would be so because this files also have to satisfy this F term constraint. So in the end, we wanted we have the statement that this is a representation of the Jacobi algebra that's defined as the path algebra divided by this F term constraint. So this F term constraint give you the equivalence between the paths. So for example, if you have let's say suppose you have all these paths here, and you see that now there are two loops here, and then these two loops share one common arrow. And suppose in your superpotential you have this term. So now let's focus on the arrows, this arrow that is shared by these two loops. So from this superpotential, I take the derivative with respect to this shared arrow. So you see that this F term constraint means that these two paths is equivalent. These two. This path and this path is equivalent. So this Jacobian algebra is a path algebra up to path equivalence. So okay, so remember that we start with the type 2A string on the toric club L3, and then we want to look at the this half BPS sector. So that's given by this dB bound states. So with this charge, some certain number of D2 and some number of D0. So this gets translated into the quiver quantum mechanics with a certain rank. So this. These numbers get translated into the rank of the gauge groups. So that means this our Carré fundamentals. They are the in a dimension representation of the this Jacobian algebra. So this toric club L3 fold. So this the toric data gets translated into the quiver data, and the different charges get translated into the rank here. So which is this one. So that means that we're looking at an a-dimensional representation of the Jacobian algebra. So now from there, I want to make the statement that you also impose the D-term condition, meaning that you specify the stability condition here, and then that this gets translated into the a codimensional ideals of this. So this part is I think the most difficult to see. So I will try to explain this one in more detail. So how do you get this finite codimensional ideals of the Jacobian?
Like in this example, can you explain what these are?
Huh?
For this thing with the path connected concatenation. Suppose
You mean for
this as a quiver.
I mean for this particular one? Yeah. So this the general case. So the general case I'll explain after I first explain the special case.
Okay.
This the special case of the toric one. So for toric one, the special thing is that this ideals and also this Jacobian algebra has some 3D crystal structure. So once you understand that, it's fairly easy to see how to. I mean, actually, you don't need to go. I mean, strictly speaking, you don't need to go through. You don't need to first understand this. You can just directly understand formulate everything in terms of the ideals. But I find it easy to think about this once you have some more geometric visualization. Okay, so I think I'll explain with this the simplest case or the next simplest case. So what's so special about the toric case? So it's special because so in this case, so you have quiver and superpotential. So for this case, you can show that in the superpotential, for each arrows, it appears exactly twice. Once with a plus sign and once with minus sign. So with this property, you can repackage this information into a periodic quiver. Meaning that I can draw this this quiver on the R2 periodically, and then so this Q2 label the phase in the fundamental domain. And so each phase will correspond to a term in the superpotential. And so along this phase, all the arrows are in the same direction. So there's a loop along this phase, and the orientation of this loop corresponds to the sign. Correspond to the sign of the term in the superpotential. I erase this again. So.
I already made it.
Okay, so I want to. So this the superpotentials I1, I2, I3 minus I1, I3, I2. So now how do I draw this periodically? So there's only one vertex. So this is, let's label the direction this way. I1, I2, I3. What's the convention? So, I mean, you can draw this, you can cover the entire plane, but this is the fundamental domain. And you see that there are two terms. So this orientation will correspond to the plus sign, and this orientation will correspond to the minus sign here in these two terms. So, so before I go on with, so in this whole construction, we actually also have to consider the framed quiver. So by framing, we mean that we introduce also additional vertex. We introduce another vertex that we call a framing vertex. And then we introduce some additional arrows that are going from the framing vertex to some vertices that's in your original quiver. Or it can also be some arrows going back. So the framing can contain many informations. I mean, it can contain the information of the stability condition. And you can also capture, say, when you can have open BPS states. Here it just means that you can have some D2 ending on D4 wrapping Lagrangian subcycles. And you can even the truncation of it can captured by the framing. So the simplest one corresponds to that there's only one arrow connecting to some vertex in your cube. So this is your original cube. So this is the framing vertex. So this one that's the vertex that the framing vertex connect to will call the framed vertex. So the simplest case that we will consider, I mean, is a situation when there's only one arrow that connecting to a particular frame vertex. So this will correspond to the case when you don't have any of all these additional decorations, and the chamber is the non-commutative DT chamber. So that means, so with this, the framing here means that all the paths have to start with this frame vertex. Or another way to say this is that you just include this frame vertex here. So they all have to start from this this framing vertex. So it's let's call this A angles. So then that gives you a projection of your Jacobian algebra. That's so this just means that you're taking all the elements of the Jacobian algebra, all the elements that start from this the frame vertex.
So you are adding an abrupt bifundamental or from infinity to the.
So this this framing vertex, it doesn't. It's a frozen vertex. It's not dynamical. It's not. There's no gauge group there.
Not like a Q0 becoming a Q0 plus 1 toric diagram. Does it become quiver diagram? This has, one more vertex added.
Yes, you have one more vertex, but this vertex is different from all the others because it's not. You're not going to introduce. So all these vertex. Remember, for each vertex we have Stefani generators. So they will generate the BPS states for you. And this one is frozen, so you're not going to introduce any generators for this, the new additional one.
Why are you doing this?
So in some sense, I have to, so this will, if you forget about all these additional decorations, at least you have to have one D6 brain to compactify the moduli space. I mean to define the stability condition better. So this framing vertex, if you don't have everything else, they will just correspond to this 1d6. And this NCDT chamber will just define the stability condition of the representation that you're considering.
What is DT?
Donaldson-Thomas.
Same Donaldson-Thomas.
Same Donaldson-Thomas.
DT just is free.
Yeah, when I think yesterday they discussed the DT invariant.
Ah,
Same
in a
DT.
different context, so I'm trying to see how it is connected here.
No, it's the same context. It's the same context. I mean, all these generating series will be the generators of the DT invariant.
Okay.
And the generating series will be the character of the algebra. Right. So now with this framing, that means that without the framing, you're drawing this let me just draw the C3 example. You have this periodic quiver, and with this framing, you're starting. So in this case, you're anyway just starting from. There's only one choice. You're starting from this vertex here, and so here you just choose, because it's periodic. So you just choose one particular one, and then so the path. So you're looking at the path up to equivalence. So you have. So say the so you can have this path, and you can have so that would be this one. So this one. So now the claim is that this path up to the equivalence in this case will correspond to the plane partitions. So you see that if I start from this the origin, and if I don't go anywhere, that corresponds to trivial path. So first I can have the trivial path. So the trivial path will correspond to the first box here, and then this the path along this first direction will correspond to this box here, and then this one corresponds to the path next to it. So this one we have 0. Here. And then you can also have another path. you first go along the second direction and then the first direction. So you see that these two will correspond to the same item here. Not that easy to draw here. So you see that these two correspond to the same box here. Is there any questions? I think I'm a bit, it's not easy to visualize here.
I have a question. Doesn't matter that this rightmost arrow is up.
The right.
Like let's say northeast arrow. This one, yeah. Ah, okay.
Sorry. So here the three direction is always
By three we go up.
by three we go up. So I want to uplift this periodic quiver to a three-dimensional crystal. So this direction, the I3 direction is up. The I1 is here and I2 is here. So you see that I start from the trivial path. That means that the path that go from the frame vertex to this one. So that means that I'm just staying at the origin. That's the first one. And this is the next one, and then I just draw this one. The one here. Is it clear?
Yeah. Yeah, we should finish for
Sorry, I go way too slow today.
We still have 2 more to go.
But somehow, I don't know why today so much.
And we ask one question.
No.
Yeah, you got me.
But I shouldn't actually stop, right?
Yeah, I think it would be good to stop for today and continue on Friday.
Okay, yeah. Is it much slower than yesterday? I didn't have coffee. That's the reason.
I think it's fine, and it also it also allows for us to digest it.
Okay.
Yeah.
Yeah, it would be easier if I explain this. Probably it would be better if